I am Ari Gesher. You probably have never heard of me. My day job, I work at a place called Kairos Aerospace, and I'll talk a little bit about that as part of the presentation. I was a very early engineer at Palantir, spent about 10 years building that company and all the data plumbing that goes along with it, and was able, while I was there, to write a book called The Architecture of Privacy, which delves into how you put privacy controls into data systems that hold information about people, especially when you have information about people without their consent. It's kind of a love letter to the NSA, like if you're going to do this, this is the way to do it. And previous to that, I also ran SourceForge.net. For the young folks who might be in the audience, that's GitHub before there was GitHub. So. And today I also serve as an advisor to a company called Jupiter, which what they do sort of makes up the core of what I really want to talk about today. But we have to sort of set the stage, right? So we live in an age of exponential amplifiers, and this is like a recent innovation in human history, right? It starts actually with the Industrial Revolution. Like before that, life was pretty linear for humans. Like you could get together a lot of people and maybe some animals and maybe a water wheel and do some stuff. And you know, if you were a king, you could get a lot of people together and they could do something. But for regular people, it was like you and the person next to you, and that's about it. But in the Industrial Revolution, we unlocked the ability to burn a bunch of carbon to do some work, right? We're like, oh, if we burn this and make some steam, we can like make a train go or whatever it is. And so that's super useful. And then what happens is that humanity goes exponential for the first time, right? And so these are like 12 different graphs of different things. And you can see they all sort of track with the middle of the 1800s. And the world just goes whoop. And most of it is tightly correlated to the population explosion. The population explosion comes from the availability of free energy to do agriculture and create things like fertilizer, something you can feed a lot more people. And the Industrial Revolution culminates in, you know, like the most powerful machine ever built, the Saturn V rocket, which sent that little tiny thing at the top all the way to the moon and got us this lovely picture called Earthrise, right? So this was shot out the window of the command module of the Apollo 8 capsule as it was in orbit around the moon. And it's one of the first images that we actually have of the entire Earth, where we can like consider the whole world as a system. That's important. We're going to come back to that. So today we live in what a lot of people are calling the second machine age, right? So this is the second time that we've gone exponential with some technology. And none of this should be news to anyone here in this room. Welcome, fish. Let me introduce you to water. This is where we live, right? Like we live on that curve of Moore's Law and its cousins around storage and telecom and all this stuff. And it culminates in something like this, which is like Intel's Xeon Phi Knight's Landing, 8 billion transistors packed into something about this big, 3 trillion floating operations per second. Software is eating the world, right? This is the adage given to us by our philosopher geek king, Mark Andreessen, that, you know, we're in an age where software is changing everything. And the reason for that, if you go back and you look at the Industrial Revolution graphs, the first steam engines actually come online in like the mid-1700s. People are like, oh, this is cool. Let's build a steam engine. What are you going to do with that? I don't know. Seems pretty cool. And so what follows is about 100 years of people messing around with the technology, making it easier to use, figuring out what to use it for. And that explosion really starts 100 years later, in the middle of the 1800s, when everything goes exponential. But this is like 100 years after this technology was invented. So there's reason to believe that maybe it's going a little bit faster this time, but not by much, because I think the thing that actually keeps back technological revolutions has to do with the speed at which human generations learn how to use stuff, not how fast the technology gets developed. So if you look at the history of computing, like starting with something like ENIAC, we have generations of larger and larger populations of people who get access to the technology, and the technology becoming easier and easier to use and apply to different problems, right? And so today, with cloud computing, we, in this room, us very special people, are the most highly leveraged humans in history, right? Who aren't like heads of state. So if you're a king, you can get everybody to go do something, right? But for us, the amount of computing power that we can bring to bear with literally just a few keystrokes is mind-blowingly unprecedented, right? And so the effect that we can have on the world with anything that involves information technology, like if we compare the by the way, this time going exponential, way different than last time. So the Saturn V rocket is very, very special. There are only a few of those built. You could compare that to like a petascale like supercomputer today. But the difference between like something that's a little more common, like an oil tanker, and regular human work output is like maybe 7 or 8 orders of magnitude. For informational technology, we're at like 13, 14, 15 orders of magnitude difference between what you can hold in your hand and what you can do in your head, right? So there's reason to believe that it's going to be way, way more profound this time. We're just in the early stages of that revolution. And what we've seen in the past 10 years is the beginnings of being able to apply all this technology to everything in the world, which is why software is eating the world and why we are the most highly leveraged humans that have ever lived, right? So what comes along with this? Well, from my perspective, what comes along with this is actually a sense of duty. If you have the ability to do all these different things, now you have a chance to kind of pick and choose what you're going to work on and what impact that you want to have on the world. So how do you do that? It's kind of there's a lot of different moving parts to it. And in thinking about this, I came across this Japanese concept called ikigai, which I hope I'm pronouncing correctly. It's one of those epitome problems. I've never heard it pronounced by someone who actually knows what the word is, right? So here they sort of break it down into a bunch of different sectors. There's like what you love, what you're good at, what you can be paid for, and what the world needs, right? And the intersection between any two of those is kind of interesting. What you love and what you're good at, that would be your passion, right? What the world needs and what you can be paid for, that's your vocation. That's how you can make money. But if you can find the overlapping of all four of those things, you get ikigai, which is this like dwelling at the top of Maslow's hierarchy of needs, to put it in Western terms, right? Find it like living a fully fulfilled life. And I think for those of us in this room, we actually have that opportunity more so than pretty much anybody in the world. Because what we do is in high demand and we can get paid to do it. If we find something that we really love to do, then it doesn't feel like work. I mean, in my early days of being a programmer, I would just turn to the person next to me and be like, don't tell anyone, but I would do this for free. I hope they keep paying us, right? So, and then if you can then intersect that with what the world needs, now like you're living a fully actualized life, right? So I showed you those first 12 graphs of the Industrial Revolution. Here's another 12 graphs that come out of the Industrial Revolution. These are sort of the unintended side effects of burning all that carbon. The rise in atmospheric concentration of things like nitrous oxide, CO2, methane, ocean ecosystems that have been depleted, global, like the number of species that have gone extinct. There's a whole mess that we've created by burning carbon. This also should not be a lot of news to you. You can sum it up in the IPCC graph here of global anthropogenic CO2 emissions. You can just, once again, going exponential, right? CO2 on its own, not really a problem. The infrared energy that it captures, that causes some changes. And so here are the most recent projections from the IPCC, right? So the blue band, some error bars on that line, that's if we stop burning carbon today, if we completely transition to renewables, do nothing, and stop leaking methane, we only gain about a degree, right? The red line is business as usual. That's nothing changes. We just keep burning everything we possibly can. And we're looking at a consensus view of about 4 degrees Celsius rise with hopefully only 2 degrees. At the top end, it's more like 5, close to 6, right? And these are the different pieces that sort of, I like this because it's a hockey stick of the atmospheric composition. But it shows all the various different pieces. Now, methane is actually a little special here. The big problem with global warming is CO2, right? So CO2, once you put it in the atmosphere, it basically stays there forever until a tree pulls it out and makes it into a tree, because that's what trees do. But other than that, it just sort of hangs around. It doesn't break down at all. Whereas methane only has an atmospheric lifetime of about 20 years before cosmic rays and other things turn it into CO2 and ozone and other things. So that said, methane absorbs 84 times the infrared energy that CO2 does, per unit weight or volume. So it absorbs a lot more energy. So it ends up being this very short-term driver of global warming, which is to say that if you suddenly removed all the excess methane that we've put in the atmosphere, the curve would bend. It wouldn't actually change in the long term, but it might buy you 100 years, right? So I've seen some estimates that say that cutting methane aggressively could cut the warming trend by ½ degree Celsius by mid-century and up to an entire degree Celsius by the end of the century. So it gives you more time to transition to things like renewables, start your geoengineering programs to pull the CO2 out of the air, or just more time to suffer as the world falls apart. But so Kairos, where my day job is, we're actually focused on methane. So methane is kind of special in that most of the methane imbalance that's created by humans actually comes from us poking holes in the ground where methane has been sitting for 60 million years and then letting it up into the atmosphere, right? And not only is it the leaking stuff coming off the infrastructure that's a problem, but what's interesting about it is that it follows a power law. So there's a bunch of little leaky seals and, like your pilot lights out or whatever, and all of that is about 10% of the excess methane. The other 90% comes from enormous leaks out on this global infrastructure that we use to bring hydrocarbons to market so that we can burn them, doesn't get visited very often. Like IoT hasn't made it out to the wilds of Alberta and things like that. And in fact, there are various problems with IoT solutions to this sort of thing. But if you can just find these big leaks fast and stop them, you can actually solve most of the problem, right? And so the founders of Kairos are physicists, and they built an airborne spectrometer designed to work in space eventually, but for now we strap it to airplanes. This is the Mark IIA methane spectrometer. The little lens is an optical camera, the big one goes to the infrared optics. And we fly around and take pictures of the Earth. We strap it to the outside of a Cessna like this. It's sort of inside that pod. That hump on the back is where the spectrometer is. There's a couple Raspberry Pi clones and a high-precision IMU in there. And we fly around and we take tracks of the ground that look like this, right? This is actually just infrared brightness. It's not a measure of methane, but it's coming off the sensor. And so we just sort of mow the lawn back and forth over oil and gas infrastructure, and occasionally we see something that looks like this, right? So we can then take that data. I mean, Kairos does its own big data thing, like where we take a couple, 20 gigabytes a day of data from an airplane and then upload it to the cloud and turn it into stuff. It's very small on the big data scale of things. But let's come back to these projections for a second. So that's one thing you can do. This is actually where the bulk of my energy is like, let's find the place where I can be most highly leveraged and make a difference in mitigating global warming. So where did this graph come from? Like, how do we have this? Like, how do we know what it's going to be in 2100? Like, what goes into that? And so there's a whole area of practice known as climate modeling. And it's grown over the years. So it started in the 60s with things like the Landsat data, and people have been building progressively more and more nuanced computing models that can run physical simulations of the Earth, right? So basically, the way these things work is you have a bunch of different models that model all different things. So this is everything that goes into today. The premier model is something called the Community Earth System Model, or CESM. And it models all these things, everything from upper level winds to ocean bottom topography, the nature of the geography, clouds, solar energy, all these things are sort of modeled. And the thing I love about this particular thing and this whole idea of building climate modeling is that it's modern day cathedral building, right? So I watched a documentary on CERN, and the people who work in the magnet shop were like, yeah, we're building a cathedral. And so they have this very European mindset of these multi-generational projects that are good for humanity that you go and work on. And like the people who work in the magnet shop, they build the world's most powerful magnets, and it's part of this enormous instrument that we can use to probe the limits of physical reality. The same is true of like LIGO, the interferometer gravity observatories that recently saw black hole collisions and are changing astronomy. That story is actually fantastic, where for 50 years, they've been like, we need a bunch of money. We're going to build an instrument. They build it, and they're like, yeah, it didn't work. We need to build a better one. We're going to need some more money. They did that for 50 years, and then finally they saw something. They're like, yeah, it worked this time. It's good. It's an amazing story of big science. But the thing that's interesting about climate modeling is that it's all software, right? There's the computing substrate that you use to actually run it, but basically it's all software, and it's all open source, and the data is all open. So there is this enormous community of people that work on this. A lot of them are scientific researchers. I'll talk a little bit about the weather research and forecasting model, which is a different model, which is a high resolution, spatially constrained model that we use to predict the weather. And there's something like 20,000 daily users of the data that comes out of that. In fact, all the weather that's predicted in the whole world comes out of the WRF and the National Weather Service and the work that was done at NOAA on that. So how do you build a simulation like this, though? So it looks something like this. You can sort of understand building, you separate, so the atmosphere is like a thin shell around this enormous sphere or misshapen potato, actually, that is the Earth. And what you do is you take that volume and you break it up into these sort of gridded volumes, right? They're smaller, lower to the Earth because the atmosphere is more dense. They get bigger as you go up because there's sort of less stuff the higher you go. But basically, you look at these volumes and you model statistically what's going on in the atmosphere, and then you find the boundary conditions between you and the next grid, and then you exchange data between those, and then you step to the next step of the simulation, and you move your way forward, right? So, and this is the original. This is like the OG big data, right? The most recent sort of high-resolution climate models are what are called CESM-LE for large ensemble. So they ran into some problems with running the original ones, which is that they're these statistical processes, and they have some variability. So they do one model run, and they like come out with like 5 degrees, and they run another one, it's like 2.5, and they're like, what's going on here? And the answer is that as they're modeling things, there's internal variability in the climate. And so there's disagreement between one model, like 2 different model runs of the same model about what it's going to be. And so what they do now is they take the same model, same sets of initial conditions, change them very, very slightly, and then run them, not concurrently, they run them serially because they don't have enough computers to run them concurrently, but they run like all 30, like in the large ensemble one, they had 30 different model runs, right? Each one took 3 weeks to complete on the Yellowstone 1.5 petaflop supercomputer that's at the Wyoming Computing Center. Each one produced about 6.6 terabytes of output, of model output, which is just the values in each one of those grids at each time step. It was 17 million hours, core hours of computing time for in total for 1,500 individual jobs. In fact, the way that they're doing this now, the amount of data they produced just for this ensemble run is bigger than like what they gave to the IPCC for the 4th climate report. So this area is actually moving very, very quickly in terms of gaining orders of magnitude of resolution and the size of what they're doing. They did some cute stuff, like here's the actual cluster. They put pictures of Yellowstone on the side. It's very nice, very nice. This cluster was actually decommissioned like 2 months ago. And I was looking at its history. It ran at something like 92% utilization for its entire history. Like this is high performance computing. I think the HPC people kind of laugh at Strata. They're like, oh yeah, you're doing big data, whatever. So this is the serious big data stuff. And as they add resolution to these models, they're able to come up with things like this. So this was an example that I picked off their webpage where they're showing this like change in a current in a couple different places by Madagascar and by the eastern seaboard, and that the lower resolution climate models that they had didn't show that level of detail, right? And so as it gets more and more subtle, we do a better job of simulating this stuff. So part of what makes these models so good is actually that you bring in ground truth. So you actually back yourself up. You can do this thing called reanalysis, where you have a little bit of data from a couple different points that you've sampled in history, either from like weather stations in like the 1800s or from like ice core samples. And then you can figure out what that means about the rest of the atmosphere and sort of back yourself into a set of initial conditions so you can start a climate run like 100 years ago or 200 years ago or even further back to do validation that the model actually does a good job of simulating the climate as observed. And that way you can have some sense of it moving forward in time. I was actually speaking to one of the climate researchers here about how much they are modeling how the atmosphere is changing. What he said was that the first derivative and the second derivative of climate change are pretty much agreed upon, and all the interesting research area is in the third derivative of how the atmosphere is changing. So it shows you just sort of how well it's put together. So I brought in an example of a sensor because it actually ties back to Earthrise. So this is Discover, which is a satellite that lives out at L1, which is a Lagrange point. So a Lagrange point is kind of a really interesting thing in orbital mechanics. It's a point where you have a balance between two astronomical bodies. So L1 is actually the point between Earth and the Sun. This is not to scale, but the point between the Earth and the Sun where the gravity balances out such that your orbital period is the same as the Earth, even though it should be faster because you're closer to the Sun. The upshot of that is that you can stick something at L1 and it basically just sits there. As far as the Earth, in terms of its Earth position, it just sits there, doesn't move, right? And so it's a great place to put a camera if you want to look at the Earth. So Discover has this camera called the Earth Polychromatic Imaging Camera, and it now takes a picture of the Earth from L1 3 times a day. And what that lets the researchers do is establish ground truth on the cloud cover, cloud height, vegetation properties, and the ultraviolet reflectivity of the Earth. I think this is cool where they slow it down to show the eclipse if it comes up. I'm not sure we'll make it that far. I'll let it play. So another company that I work for as an advisor is a company called Jupiter Intel. And they've put together a business model that you couldn't have done 5 years ago, which is selling climate data. So basically data sets about extreme weather events that are going to happen in the future. And so if you're a city or a chief resiliency officer for a state, or someone who owns a hotel chain, you're thinking about building big properties, or an insurance company, you're interested in what's going to happen on this beach in 20 years. Like, what is the sea level rise going to be? What is the rainfall going to be? What are the chances of flood? So this is what Jupiter does. You can find that video online, by the way, if we didn't see the eclipse. So, and they are sort of using the data exhaust of this climate modeling to do what they do. So to understand, they take the output of CMS-LE of these large ensemble climate runs, and they start with a geographical area. You take like the city of Charleston, and you're like, are we going to have extreme weather events? Like, is it going to rain a lot in Charleston over the next 20 years? If so, where and when? And so they go through the runs from the climate data. They figure out, and you can see that has like 100-kilometer grid spacing, so these very large volumes. And they look for the set of conditions that lead to extreme weather events. So the climate models don't really do the weather, but they can tell you how much moisture is there, what the pressure is, stuff like that, enough that you can use that as initial conditions for a high-resolution weather run. And so what they've done now is they have built a bunch of Dockerized model runners that they can put up in the cloud. They troll through the CMS data to find things that they care about for a particular locality, and then they launch a whole ensemble of WRF simulators that will then go and step through to find out, did this cause a massive, massive rainstorm, or did it pass by, right? And they do that, they sort of do the same thing. They run 500 of them. They look at the distribution. It's very similar to like a Monte Carlo to some degree, where you have many different runs, and then from that you get back a distribution of answers that you then use to build the data set. So this is sort of the architecture that they use to do this. You can see the things in blue are things that they're leveraging from the climate community. So the reanalysis, the runs, the climate forecasting runs, those are inputs into the Jupyter platform, as well as the observational data about what actually happened that you use to understand the veracity of what's going on. And so their faculty come together and build models of the climate factors that go to create local hazards. So what level of moisture do you need in the atmosphere before you have an extreme rain event? And then they can go and scan for whether or not it actually happened. So they can go look and they can find a point in history where the model shows that those conditions, run their simulations, and see if it matches the recorded history. And that gives them the veracity of what they're doing. And then, sort of borrowing a term from marketing, they can do lookalikes, right? So they look for events like that in the future. So now they know what the signature looks like in the data in the past, and they can go run forward to times when there are similar atmospheric conditions, and then just for those periods of time do they launch a model run into public cloud to actually model that particular area. It's very cool, and there's a couple different products that they're putting together to do this. One is looking at rainfall. So this is a WRF output, not from Jupyter. This is actually a blizzard that happened in Minnesota. But this is the kind of output that WRF creates, where you can see this is accumulated snowfall that you can see for a period of time. It gets pretty, some parts are getting like 18 inches of accumulated snowfall. If you're not from the Midwest, that sounds like a lot. If you're from the Midwest, it sounds like a medium amount. They're also looking at things like flooding. So this is Charleston, a projection of an extreme flooding event that could happen in the next 20 years or so, and the amount of Charleston that would be flooded by that. And this actually is output from there. And this is actually a place where Kairos and works together. This is actually a large-scale thermal IR heat map of Glendale, of Los Angeles. This is used to understand the possibility of extreme heat events, like heat waves, which cause a lot of people to die, cause problems with livestock, and that sort of thing. As usual, when I give these talks, I have gone much faster than when I practiced it, which is good, because hopefully it kept you all awake. So this is the end of the prepared material that I have, but I'm happy to dive into any of these various topics that I've talked about if people have questions. And then, because we have a few extra minutes, you can be the first ones in line for lunch. So everybody wins, right? And then I do want to remind you, though, that I want you to come away with this call to action to go dent the world, and because we're software people, from the comfort of your couch. Okay, so questions? Yes?
So in your experience, do you have a perspective on how you can communicate data to businesses in a way that you're speaking risk in their language? How do you convert this type of insight into risk analysis that business?
Yeah, that's a good question. I mean, the basic question is how do you communicate risk analysis to businesses? Jupiter is lucky in that their set of customers are people who are doing risk analysis and are hungry for this data and can't get it anywhere else. So I'm going to punt on that because the answer is they already know. They already have risk models. And in fact, part of the product design here is you have the model runs, they're going to produce a bunch of data about what happens, and then the size of the relationship between Jupiter and its customers is big enough that it's easy enough to tailor that, to say, well, what models are you using, and what form would you like the data in? And so if we have to add an extra rendering step of that data, it's easy enough to do. So a lot of that ends up being sort of bespoke integration that can happen on the Jupiter side.
So if I could follow up, could you give any examples of what are some things that businesses have really wanted to know about in terms of storm risk or climate change risk?
Yeah, sea level rise is a big one, as well as rainfall, because both of those lead to flooding, which is incredible, property damage and danger. The heat score one is coming up. The other one that people have been interested in, and Jupiter is at least looking into, is extreme weather events in terms of being able to forecast the magnitude of a hurricane very, very quickly. So rather than looking tens or hundreds of years in the future or whatever, not hundreds, but tens of years in the future, it's looking days in the future to understand what the risk is from a hurricane and predicting its track better than has been done previously. Over here.
Two questions. The
Sure.
first is, I assume a lot of this, of the customers that consume the Jupiter's data are insurance companies, like you mentioned.
Yeah.
Are any heads of states involved or interested in?
So the interesting thing about this kind of data from a governmental perspective is that usually it's all done locally. The question was, of course, there's interest from people who care about risk, like insurance companies, but do heads of state care about it? They probably do. I don't know that they're the direct consumers. The people who, like, what Jupiter's offering is not long-term forecasts about what's going to happen to the whole world or a whole nation. It's literally like down to like a very small area, and so that tends to be much more interesting to people in local government. And what I've seen from previous work that I've done at Palantir and elsewhere is that a lot of that resiliency work is being done by local governments. And so the places where you're getting chief resiliency officers as part of government are like Norfolk, Virginia is actually one of the leaders there, where they're very worried about sea level rise. New York is doing a lot of very good work on this. So there is definitely interest, but it's usually not at the national level. At the national level, you're looking at the climate simulations to do things like setting policy. This situation is evolving as people's understanding of what the problems are and how to deal with it are. So it may change in the future, but for now, it's sort of much more tactical, as it were.
Awesome. And then my second question, thank you for that. I have a background in simulation in the physical sciences. Could you touch on the technologies that are used to implement these models?
I could if I knew a lot about that. So the technologies that are actually used to implement these models, I mean, it's a lot of floating point. I don't know the details of the climate models. My background is a lot more in the sort of data plumbing and orchestration side of things, and so I can say that like they pull the data out of those climate runs, they'll pull it up into public cloud storage so that they can actually like classify the events that they want to look at. And then the rest of it is just sort of doing large scale cluster scheduling, where they'll launch, like the WRF runs, they'll take, I think they said it takes about 3 or 4 hours for the less detailed runs to run. Some of the longer runs will take about 20 hours. But because you're on public cloud and because you're doing container scheduling, it's really easy to be like, all right, this machine's going to do these 5 runs. You just use software to parcel it all out, and then when you're done, you shut them all down, and all the data is sitting in your object store. But yeah, the numerical simulation piece it's a whole world unto itself. And a lot of what is going on here is the repurposing of those sort of technological artifacts into new forms that answer new questions without really going and changing that simulation. Now, Jupyter is working on changing the nature of those simulations, and in fact has pulled a bunch of what are essentially faculty out of places like NCAR, the National Center for Atmospheric Research, to come in and enhance their models with various different things. And then the other thing that's really coming into changing this is the use of machine learning, both to find like those lookalikes, but also to validate your models in real time. So like you have some model, you've made some prediction, and like 6 months later, you want to look at the sensor data to make sure that it's actually matching what's going on. If not, you want to revise the models, right?
Just to follow that up sort of the other direction, is there any, like, what's the best place to sort of get started at a small scale, to sort of playing with this stuff to get a sense of how these things work? That's always been, it's really cool to see these large clusters, but it'd be cool just to get a better sense of how these models work. And like you said, like working from your own couch, like where's a good place to start looking to start playing with?
I would start with WRF.
Okay.
It's actually very well understood. There's a lot of documentation. There's a huge community around running it. And like you start with a set of initial conditions, you run the code and it spits this stuff out, and then there's things to visualize, like
Awesome.
what the temperature would be and all that stuff. So if you look up, WRF.
WRF, awesome.
Yeah.
Thank you so much.
Yeah.
Is there the concern that the lookalikes of the past don't represent the future?
So the question is there a concern that the lookalikes of the past don't represent the future? Not a huge concern. I mean, like, look, anytime you're forecasting the future is the question of like, how do you know what's going to happen? No one knows, right? Using this approach, which basically says, let's find when local atmospheric conditions will cause weather, right? So weather is a phenomenon that happens like locally in space and time. Climate is a global thing that happens as sort of an evolution. And so the climate models are only predicting the atmospheric conditions that might lead to these extreme events, right? And then to defray the risk of like a single model run saying, oh my goodness, this is going to create a huge rainstorm, and then the next run that you do not doing that. That's why they actually run a very large ensemble of the models and then pull from the distribution. So you run 500 of them. If 400 of them converge to a huge storm, and then 100 of them have some other outcomes, you can say that the likelihood of the rainfall is actually very high. Now, what Jupyter is doing, so there is a company that you may have heard about called Climate Corporation, and they were looking to do like micro-targeted forecasting, like to tell you in this week in March next year, this is how much rain you're going to get. This is not really what Jupyter's doing. So Jupyter's really, like the data that they're providing is much more integrative. It's not about on what date in the future will there be rain, but for that year in the future, how much rain can you expect, and what is the likelihood of there being an extreme weather event, right? And so because what's being delivered is actually statistics and probabilities, by using a large ensemble, you get convergence from your models, and then the actual precision isn't so important so much as the integrated values that you come up with about the characterization of what the weather will be. No. So the question is Jupyter a product of Kairos? No. Two completely separate companies, but two companies both using various parts of data machinery to try to mitigate the effects of climate change. So in the case of Jupyter, this is the way that you actually change human behavior. So in absent government intervention and things like carbon taxes, the way that you get people to change their behavior is you start bringing climate in as a pricing signal. Right? And so by getting this data to insurance companies, by getting it to real estate developers, by getting it to cities who are going to set regulations about things and building codes and things like that, you suddenly start seeing the climate signal show up in the economy, which turns out to be a great way to change human behavior by like putting a price on it, right? Rather than saying, you should really do this because it's going to be bad later, which nobody cares about, right? But if you say, hey, this is more expensive, human behavior will change. Well, in this case, like I think overfitting. So the question was like, do you run a risk of overfitting by running the weather model? So there's sort of this pass through the climate modeling data to just find predicted atmospheric conditions that might lead to extreme weather events. And then the way that you get away from overfitting is that like you're not actually like you look for situations in the past. This may relate to sort of your question as well, which is like it actually doesn't matter how the climate has changed overall. If in this particular 100-kilometer cube of atmosphere you have these conditions, this amount of energy, this amount of moisture, so on and so forth, it should behave the same. It doesn't really, like unless there's some missing variable, right, in what's going on, it should behave the same. And there's so much attention paid to backtesting this stuff against, like, so like they'll take a climate model, they'll run it, you know, for the previous 100 years, and then test those conditions and see if the output of the models agree with recorded history. But because they're physical simulations, air is air. Like even though we're adding more energy to the overall system, for an isolated portion of it, those conditions should hold. And so I think the risk of overfitting is fairly low. I think the risk is actually the opposite, which is that by only doing a single model run, there's a lot of variation in these chaotic systems. And so you actually have to do this large ensemble run to understand what the distribution of outcomes is rather than a set prediction about what will happen. Yeah, are you talking about this slide way back? Yeah. This one? Yeah. So this like allows you to. I mean, there is, I guess, some risk of overfitting, but like in some ways, you want to overfit or not overfit, but you want to fit to the actual physical system in the atmosphere. And so places where, like, you're looking for places where the model doesn't take into account what's going on, and by bringing in the sensor data and the recorded history, you get to actually correct it, right? You can almost look at it as like it's similar to like a validation set in machine learning, right?
Hi, thank you. So I'm assuming weather is a chaotic system, and you showed us some hockey stick graphs. When you do those back tests, how do you get those conditions? How do you map? You know,
how do you get the initial conditions?
Right.
That's actually, so see reanalysis there. So like you only need so there's two sets of initial conditions that you need, right? So like you can think about this as you're running a very large scale climate model, and you're running that at sort of a very coarse resolution, right? And to run the climate model, you need initial conditions. Part of the way that they get initial conditions is they have an understanding of the atmospheric dynamics, and then you start with ground observations at various points in the world, and from there you can infer the initial conditions of the atmosphere based on your understanding of how it changes, and that gives you the beginning state for a climate model run, right? And what they're doing now with the climate model runs is you run a bunch of them. They are chaotic. There is divergence. There's a sort of internal climate variability. There's actually a great paper if you go look for CEM's LE, there's a paper on why they did it this way, this large ensemble thing, and why they had to like literally raise a couple orders of magnitude the amount of computing they put into it, is that they wanted to do 30 or 40 runs of this, it's a 180-year simulation of the atmosphere, right? So you do 30 or 40 runs, and then that's what gives you your error bars. So you'll see that there are potentially different outcomes. From the Jupiter perspective, they look at all of them. They don't care, like each one of the ensemble is a different way that the atmosphere might go. And then anytime it obtains the initial conditions that might lead to an extreme weather event, then you run the weather model, but you're running the weather model on exactly how it's supposed to be run, on a very short temporal scale. So you're saying, okay, there's this much pressure, energy, and water in the atmosphere over Charlotte today in 2051, right? Now let's run WRF and see if it rains in the next 3 days. And we know that the weather models work really well. Like, I mean, they forecast the weather, and the forecasting actually works very well. And then you run an ensemble of those as well so that the variability in those chaotic systems then gets smoothed out into a distribution. All right. Oh, one more, or another one.
Cool. It's probably the last one. Thanks. This was a really interesting talk.
Thank you.
I'm wondering if
Jupiter has made any predictions about how the local climate will change here in California, for example, with regard to the Sierra snowpack or forest fire risk?
Yeah, I believe that smoke is on the roadmap. Like smoke from wildfires, which is actually is one of the things that you can actually look at, and I've seen some atmospheric models that look specifically at that. I think there's something called I think it's WRF Chem, or maybe it's CMS Chem, which looks specifically at some of that stuff. The snowpack is taken into account by the climate models, so that is actually a big part of what's going on. And in fact, I had a note here on that I can see, but that this approach has actually led to better advances in modeling sea ice, and it's revised upwards the upper ranges of expected sea level rise. Right, sea ice is a little bit different than snowpack, but like that is actually taken into account in the climate models. Jupiter is not looking at the world writ large. Right, so it's a very different, like it really is something that exists as a useful thing in the world, but in the data exhaust of this larger scientific effort, right? So the scientific effort is to understand how climate is changing, and that includes things like the snowpack. And then once there's a customer who cares about a locality and has a particular question, then those models are run to answer those particular questions. So you could, but I don't know that it has been. Okay, thanks everyone.
Thanks very much.